Good morning, everybody. It is 10 a.m. We'll get started. My name is Travis Callan, a senior sales engineer at Long Building Technologies, focusing on data centers. Today, our subject is high density cooling for data centers with Munters. As our rack densities start to grow, we have to get creative and find ways to dissipate the heat out of our server racks, and that's where Munters comes in. Today, we have Andrew Martin, who is the sales manager for the Munters data center side. Andrew, thank you so much for joining us.
Travis, thank you for having
Glad
me.
to have you. Take it away, my friend.
All right. So as Travis mentioned, I'm Andrew Martin here with Munters High Density Cooling. I represent the data center cooling technologies section of Munters. We have a few business units, but our business units focus solely on data center cooling. So the ideas I want to go through today are the as is for air cooling, and then what we're doing to change that, and then a little bit about the Munters offering. So some of you may already be familiar with this. The standard setup we're seeing today is, let's say, an air-cooled rack using server fans to dissipate heat, pulling air from the racks, bringing that into hot aisle containment, pulling that back to chilled water fan arrays, bringing that up to the rooftop for ejection. So that's good and all. And here's a sample layout of what that looks like. So you have the racks here, you have your air flowing across it here, coming back to CRAWs, coming back to a facility water loop, and then going to an air-cooled chiller. Notice my product placement here and these beautiful graphics here. There's an issue with this. So you've probably seen it because it's been in the news cycle for data centers every day for the past year. Densities are going up. This little thing called AI seems to be a big market mover. And companies like NVIDIA are coming out with chips that are pushing racks well beyond the historical 10, 20 kilowatts per rack. We're seeing 100 kilowatts per rack, 200 kilowatts per rack, 300 kilowatts per rack. They're talking about 400 kilowatts per rack coming at the end of next year. So these numbers are going up. It does seem like this is here to stay. This is starting to dominate the market. And there's a problem with air cooling. So when you get above about 40 kilowatts per rack, you start needing to push more and more airflow through the racks. You don't want to bring your aisle air velocity above about 600 feet per minute. You start starving the racks. You can start widening the corridors, put in more powerful fans, run a higher delta T across your racks. And that could get you up to the 60, 80, maybe even 100 kilowatts per rack with air cooling. But you're going to get diminishing returns. Your energy numbers are really going to suffer, and your reliability is probably going to suffer as well. And then on the flip side, our decision gets made a little bit easier because manufacturers like NVIDIA coming out and saying that, hey, you must air cool our chips. So when somebody like NVIDIA says something like that, generally us in the market, we follow them. So that's one of the major reasons we're having to switch to higher density cooling. The first one I want to talk about, there are a few different strategies, but the first one I want to talk about is direct chip liquid cooling, and specifically here, single phase. So no evaporation taking place and direct chip liquid cooling. So about 80% of the heat generation inside of these new generations of racks comes from the CPUs and the GPUs. And so the goal here is you put a cold plate on top of the CPU and or the GPU. You bring in slightly chilled water. You absorb about 18, 20 degree delta T across the cold plate, and you reject it out to a CDU to cool. Note that you still do need a degree of air cooling here because while your cold plates are on your CPU and or your GPU, your other things like your memory, your capacitors, your network gear, and your rack, those are not receiving liquid cooling. Those still do need air cooling. So about 20% air, 80% liquid is generally what we're seeing on the new generation rack design. Those numbers fluctuate, but that said, the CRAWs that are existing today, will not be, let's say, going away. Air cooling will continue to exist at least for the current foreseeable future. So let's start at the chip level. If you have a cold plate at the chip, looks like a CPU and a GPU here, both being cooled by a cool liquid coming in, absorbing heat from the cold plate on the chip itself, being rejected, and then back elsewhere outside into your infrastructure. So in this case, we're using external CDUs. We have the piping inside the rack, the tubing, taking all of this water. Usually it's 25% propylene glycol water, Dow Frost. And that's actually generally for the chemical concerns and the let's say, bio concerns. They're not so concerned about this freezing. CDUs, so coolant distribution unit, can be internal or external to the racks. We as Munters, we recommend external to the rack. There is a time and place for internal to the rack, but for scalable, high density solutions, we always recommend building out a technology cooling system loop, a TCS loop, or IT water, technology water. You'll hear it referred to in a lot of different ways, but the TCS loop running to external CDUs, of course, with redundancy. So a little bit about those loops. This is notably different from the facility water. So this is not your chiller water running directly into your racks. We often get the question, why don't we run the chiller water directly into the racks? There are a few good reasons. It's a good question, and maybe you gain some efficiency from doing it. But the first one is filtration. Naturally, you don't want leaks inside of your racks. Water plus expensive IT equipment is a disaster. I think we all know that. And your chances of a leak with dirty liquid goes up. You get clogs, you get pressure points, and you get much more likelihood for leaking. So 25 to 50 micron filtration within the technology loop has been common. We're actually seeing more on the lower end, 25 microns being more common now. Everybody is pretty strict about this. There's also the control aspect of it, both from the pressure and flow rate and the temperature control. This is a relatively small self-contained loop here. The blast radius of a leak would be much smaller than if you were to run your entire facility water loop and have it, let's say, all of that flow passing through here. So a lot of work is done with shutoff valves to limit the blast radius here. And then there's the temperature control aspect. Naturally, with a big old facility water loop, modulating that temperature takes significant energy and time. And with a much smaller loop, you're able to modulate that temperature much more precisely. Something like an 18-degree delta T, 18 to 20 is the most common in our experience. Depends on the flow rate, but we've seen up to 27. We've seen maybe down to 15 through these two. So these numbers seem to fluctuate based on the project. So if we take the as-is graphic from before, and we bring that into a as-is becoming right now, here's a relatively simplified implementation. As before, there was no internal water loop, a technology water loop. It's becoming very common to bring in your water loop inside the white space, bring it directly to the racks, and that is inherent to liquid cooling. So we start there, bring it to some CDUs, coolant distribution units. You still have your CRAWs, you still have CRAW capacity, and then you're still coming out to a facility water loop going to air-cooled chillers. I do note that this is overly simplified, and this may be applicable for some retrofits where people are pivoting mid-build, let's say, deciding they need liquid cooling in the middle of their installation, pulling out CRAWs and dropping in CDUs in place of CRAWs, and using one facility water loop to service it all. It is a fine solution. I will note that from the Munters recommendation and generally from an efficiency standpoint, it is much more effective to have a separate water loop feeding CDUs. Generally, the CRAW temperatures, operation temperatures, and the CDU operation temperatures are very different. And so you're losing out on potential efficiency if you're using one loop here to service it all. So that said, when it comes to direct-to-chip liquid cooling, this may be the most common solution today. It's not the only solution. There are some very popular solutions as well. This one being of a similar flavor, but more of a, let's say, a Munters flavor. There aren't as many people in the market doing this as people like Munters. So from the right-hand side here, you're still keeping a technology loop. You're still running your water directly into the racks. This is still that 25% propylene glycol. What's different is everything from the left on outward here. So instead of running a facility water loop like you will with your chiller, this is all refrigerant lines. And so these are one-to-one refrigerant runs. This is a rooftop condenser running down to with a one-to-one run to a fan array evaporator. So this is like a chill water coil, but it's evaporating refrigerant. This LCE, liquid cooled evaporator, it's like a CDU, except it's water on this side, refrigerant on this side. A couple reasons this is beneficial. The first one, always with refrigerant, maybe not always, but with refrigerant, you're able to get a much tighter approach temperature, which allows you to perform much better free cooling. Uh, you might often hear that free cooling is only for Chicago and the Arctic Circle, but with refrigerant-based systems, you can get a very tight approach. And even in the days of air cooling last year, you can get very good free cooling numbers in the Dallas, the Atlanta, the Kansas Cities of the world. It's really only when you get down into the Arizonas of the US that you really start to struggle getting any free cooling throughout the year. Another reason is the infrastructure reduction, especially for pivots and retrofits. If they've designed their chilled water loop a certain way and suddenly they need to add liquid cooling, you're faced with two choices. A, you beef up your facility water loop pretty significantly to get for the extra capacity, to add for extra capacity. Because your racks are more dense, you're going to have more total capacity within this rack. Or you add a second facility water loop, which is more efficient to treat the CDU specifically. Both of those are, let's say, burdensome from an infrastructure perspective, and it's been a very popular solution in our experience. Take an existing 10 megawatt build, looking to add another 10 megawatts of liquid cooling, not needing to add a second facility water loop and running these direct refrigerant lines. These are low pressure, gravity fed refrigerant lines, comparatively very cheap to install, especially next to a full chilled water facility layout. There are more. For example, there is a half measure. If, for example, colocation companies looking at customers wanting to bring in liquid cooled racks into their data center space, but they're not willing or they don't have the capabilities to install a technology loop. Do they have any other options? The answer is yes. This is one example of a rear door heat exchanger. We call it liquid assisted air cooling. This isn't a Munters product, but I like to show it to show that there are solutions. So your rack here, you still have liquid cooled servers. That's still liquid running to your cold plates here. But instead of rejecting out to a water loop, you're rejecting it to a heat exchanger adjacent to the rack. So your delta T on your air goes up pretty significantly. Your energy needed still goes up pretty significantly because there's a lot more density in the rack naturally. But you do not need the liquid cooling infrastructure. Good solution for an interim. What we're seeing is that this is pretty limited on the total density you can get inside of a rack. We don't expect to be able to reach 250, 300 kilowatts per rack with a solution like this. So for the interim, let's say a good half measure without the complete infrastructure commitments. And then everything I've mentioned so far in direct-to-chip has been single-phase direct-to-chip. There's also two-phase direct-to-chip. This isn't as widely adopted yet. This is more of an up-and-coming technology. And the first question is, well, why? Why would you use two-phase instead of single-phase? The rest of the market's going with water. Why not stick with the rest of the market? Three good answers. The first one is this refrigerant is dielectric fluid. If this leaks inside of your cold plate, inside of your rack, it's an inconvenience. If water leaks inside of your rack, you're likely destroying everything inside of that rack and costing a lot of money. Whereas refrigerant, you do not want this to leak in general because it's inconvenient, but it will not destroy your equipment. So that's one aspect. Another aspect is, again, the better approach temperature on refrigerant. So in this case, this is a pure refrigerant system. Rooftop condenser, bringing the refrigerant down to the racks. I need to speed up. So, all right, rooftop refrigerant running down to the racks, being evaporated to the cold plate and coming back up. So much better approach temperature, and naturally this is a zero water system. So zero water consumed, zero water installed. So for any customers looking for a true wireless installation, the solutions are out there in the style of two-phase direct-to-chip. And I do need to mention technologies that have been out there for a while, but have never seen a massive adoption, being immersion cooling. There's single phase and two phase. We won't talk too deeply about these because these are not necessarily adopted by the market still en masse. Just like we were afraid of liquid cooling, even last year, 2 years ago, most people in the market are still very hesitant to move forward with immersion cooling. But that's not to say this might not be popular in the future. We as Munters, we're agnostic towards it. That's okay, but we would like to support it if the customer wants to go this way. There's no air cooling component, which makes this pretty attractive. So for the sales part of this, where does Munters comes in? So we do virtually everything outside of the server dissipation. So we do partner with ZutaCore, who builds cold plates. But when it comes to CDUs, whether it's water to water or water to refrigerant, CRAWs being water to air or refrigerant to air, and just about everything you can put up on the rooftop. We don't do cooling towers, but we do dry coolers, we do chillers, we do rooftop condensers, we do evaporative systems. And really, you can break down our systems. I'll jump quickly through here into three sections. You have your chill water solutions, which is chillers and everything associated with it. You have your refrigerant-based systems, and you have your evaporative systems. So chillers, very quickly, everything associated with a chiller. You have your rooftop chiller, air-cooled or water-cooled, going down to CDUs and or CRAWs. We build Geoclima is the name of our chiller line, mag bearing, very high efficiency, tight footprint, lots of capacity in a very small space. Dry coolers as well, same concept. So CDUs and CRAWs, I won't talk about too deeply here for the sake of time. Then chilled water, refrigerant-based system, conceptually quite similar, but again, it's refrigerant running through here, not your chilled water loop. Very good for minimal infrastructure, very good for free cooling. Whereas the mag-bearing chillers are going to be best in class for high ambient, peak power reduction, and just running basically without economization full year round at very good numbers. Your side cool systems are designed from the ground up, free cooling, economization. So you'll have a larger footprint, potentially more expensive equipment, but your install costs are going to go down very significantly, and your annualized numbers go up crazy good, especially when we come into liquid cooling. Lastly, evaporative systems. I won't go through my numbers here, but imagine this, 96.7% of the annual ton hours being purely fan energy. Compressors running about 3.3% of ton hours for the year. That's why we go for a refrigerant system. That's why we put so much effort into free cooling. And lastly, evaporative. This is no longer a popular solution, but this was sort of what got us into data centers as Munters. We've been doing evaporative media for maybe close to 60 years. And it was very attractive to customers at first to consume very little energy by evaporating water instead. So I do mention this because this is close to our heart as Munters, but actually we're seeing very few new requests for evaporative-based systems. Of course, naturally, you can make very good arguments in places where you have water. This is a very large hyperscale install using pure direct evaporative cooling. Very good, very efficient water consumption, very good cooling. But again, you're consuming a pretty significant amount of water. And lastly, humidifiers. I touched on these very briefly because we do data center humidification, which is not as popular as it used to be because the envelope has grown pretty significantly in what you're allowed. But I do like to mention that as well. And one more time back to our chart. And I'm probably over time, and I'll pass it back to Travis.
All good. Thank you, Andrew, very much. I appreciate it, partner. We have a $100 Topgolf gift card, a 4K drone with camera, or a Fitbit Inspire 3. Join us next week with Austin Whiteley, where we're going to talk about custom modifications with Moss HVAC. Thank you all very much. Hope you all have a great day.
Thanks, gentlemen. Thanks, Travis.
Thank you.